Hey guys, so in the last video we saw how to derive the gradients of the parameters with respect to the loss function of a single layer perceptron, which means it had only one layer, one output layer and one input layer. Now in this video we'll be having an extra layer, so the neural network looks like this. This is a shallow neural network, so that means it has one input layer, one hidden layer and one output layer. Now in this video, we'll be seeing how to calculate the gradients of the parameters. Let's get started. So for the last problem, we didn't actually use any vectorized implementation, but for this shallow neural network, we'll actually be using vectorized implementation. So what that means is each layer will be considered as a vector. For this video, I've used the input layer, which is A0, to be n cross m. So that means we have n number of features and m number of examples. Now we have only one example, we are considering n to be 2, and then we have only one example. So the shape of in the input layer is 2, 1, which is specified here. Alright, so the next layer we want A1 to have 2 neurons. So again, the shapes of all the activation layers should be in the same format. So we want A1 to be in the format of n, m. So n is the number of neurons and m is the total number of examples, which is 1 in our case for the purpose of this video. We want A2 to be the output layer, which has only one neuron, and this follows the same convention n, m. So we have 1, 1. So I've put these three here for your reference. A0 is 2, 1, A1 is 2, 1, and A2 is 1, 1, and it is in the format of n, m. Now let's look at the weights. As you can see, the weights are represented by the blue lines here. So the straight line represents the weight associated with this neuron, and the curvy lines represent the weights associated with this neuron. And similarly, we have weights for the next layer. To find the shape of this parameter W1, we follow a convention, which is we follow the number of neurons in this activation layer, the first activation layer, which is, so we want only the number of neurons, and then next we want the number of neurons in the previous layer, which is 0. So now in this layer we have 2 neurons, and in this layer we have 2 neurons. So that is the shape of the parameter W1. Similarly, for W2, we have one neuron here. So if you look here, you have one here, and then we have 2 neurons here. So we have 2. So that makes the shape of W2 1, 2. So in general, W of L will be number of neurons in A of L, comma, number of neurons in A of L minus 1. So now we are done with defining the input layer, the hidden layer and the output layer, and we are done with defining the shapes of W1 and W2. Now we have B1 and B2. B is nothing but bias. So bias follows the same convention as A1 and A2, and they have similar shapes as A1 and A2. So if you look at A1, we have 2, 1. So B of 1, which means bias to this layer is of the same shape. So to give you a better idea, if we have this neurons to be something like 2, 3, and biases are like 1, 1, so these just add up to be 3, 4.
So biases do this work. They add some constant value to the output of the activation layer.
Now we will compute the derivatives dw1, db1, dw2 and db2. I've used the term d here, but actually it is dou and not d. Dou refers to partial differentiation, which means you differentiate the term that has the variable and treat the rest as constants. So it is always a good practice to compute the derivatives from the last. So we initially are going to compute the derivatives of w2 first, and then we will be computing the derivatives of w1. Okay, so I have rewritten the diagram to be something like this. As you can see, we have w1 here and b1 here. So the first task is to compute the derivative of this parameter w2. dw2, which is nothing but dl, the gradient of the loss function with respect to w2. Using chain rule, we come backwards. We find the gradient of the loss function with respect to a2, loss function with respect to a2, and then the derivative of the activation function with respect to z. Note that here the activation function is sigmoid, and then the derivation, the gradient of z2 with respect to w2. If you cancel these terms out, you will end up with dl by dw2, which is the final answer. If you take a better look at this, this is exactly same as the logistic regression unit, and we derived the whole gradient in the last video. So in the last video we computed the gradient of the weight w, which had 2 input units and then 1 output unit. So the link for that video will be in the description below, and you can check it out if you haven't. Now for this video, I won't be going into the detail of how to compute the gradients of w2 as it is the same answer that we computed earlier. But I'll give you a small recap of the answers from the previous video. The derivative of the loss function with respect to the activation function is 1 minus y by 1 minus a minus y by a. So this is the answer for the derivative of the loss function with respect to the activation function. And for the derivative of sigmoid function, we had an answer like a into 1 minus a. If you combine these two, you get a minus y, but since we have a2 here, we are going to write it as a2 minus y. Now coming to the gradient of z with respect to w2. So you see in this function z2, we have a1 multiplied with w2. So we are partially differentiating z2 with respect to w2, which means the term w2 will be differentiated, but any other term that is in the function will be considered as a constant. So this will give you a value of a1 because it is in multiplication. So the final answer for dw2 is a1. Now there is an important task for us. We have to verify that if this answer is correct, if this answer provides us with the answer that we need. So how do we do that? We use the shapes to verify if the answer is correct. So you can see the shapes here. You have a2 to be 1, 1, and you have y to be 1, 1. So a2 minus y will give you 1, 1, and then we are multiplying it with a1. a1 is 2, 1. Now if you see dw2, we are actually computing the gradients for dw2, right? So the gradient of dw2 should be of the same shape as w2. The shape of w2 is 1, 2, but if you perform the multiplication here, you won't get 1 comma 2, you will get 2 comma 1. So what do? We transpose this. We transpose this and make it 1 comma 2. Now if you perform matrix multiplication, you will get 1 comma 2. And this 1 comma 2 will be of the same shape as the weight dw2. So the shape of w2 will be equal to the shape of dw2. Now we can cross this off here. We have computed the dw2 term here. Cross it off. Now we are at db2. So db2 is basically the same thing. You are computing the loss function with respect to a2, and then you are computing dz2, which we just saw to be equal to a2 minus y, and then we are differentiating z2 with respect to b2. When you differentiate this function with respect to b, we get 1. So the answer is, now for us to verify the shape of b2 is equal to 1 comma 1. Shape of a2 is 1 comma 1. Shape of y1 is 1 comma 1. Is equal to 1 comma 1. So this shapes match. So now we have computed db2. Now since we have computed the gradients for weights and bias of layer 2, we go to layer 1. Okay, now our objective is to find dw1, which is here. So this is also written as gradient of the loss function with respect to dw1. So this is a long way there. You have to get started from the loss function and then differentiate the loss function with respect to a2, and then come back here, differentiate a2 with respect to z2, and then come back here, differentiate z2 with respect to a1, and then come back here, differentiate a1 with respect to z1, and then finally arrive at differentiate z1 with respect to w1. So this looks like a very big problem, but it is pretty simple. Now we have already computed this term to be equal to a2 minus y. Okay, so a2 minus y. What is a2 minus y? a2 minus y is dz, which is the differentiation of the second activation layer z, and its shape is 1 comma 1. So z2's shape is, z2 and a2 are the same thing. Alright, so z2 shape is 1 comma 1. Now we have a2 minus y, which is the derivative of z2. So it has this shape 1 comma 1 minus 1 comma 1, 1 comma 1 minus 1 comma 1. This gives you 1 comma 1. So z2 shape is 1 comma 1. dz2 shape is 1 comma 1. We have verified this. Now this portion is done. Let's go to the next portion. The next portion is the gradient of dz2 with respect to a1. So when you differentiate this function with respect to a1, this term is 0 and this term you only are left with W2. So W2. Now what are we computing here? So this whole term here is nothing but the gradient of the loss function with respect to the activation of the first layer. Alright, so we take this, we write the shape of activation of 1 is equal to, we take it from here, 2 and 1, 2 and 1. Now we are about to compute the shape of DA1. This should be square brackets. We haven't computed it yet. So we got the answer W2, and we are writing the shape of W2. Shape of W2 is 1, 2. So 1, 2. We have 1, 1 here. We have 1, 2 here. If you perform matrix multiplication here between these two terms, 1, 1 and 1, 2, you will have a term which is 1, 2. Alright, but the term that we are looking for should be in the shape of 2, 1. So what do? We can either do matrix multiplication of 1, 1 and 1, 2, which will give us 1, 2, and then transpose this to 2, 1. So that way we will get this whole term to be 2, 1, which is the answer that we need. This should be 2, 1. So this is one way. The other way is that you can take this 1, 2 and transpose it first. So that gives us 2, 1. So W2 transpose. Okay, and then you are multiplying it with this term 1, 1. So this way also you get 2, 1. If you are wondering if the answers might vary, I'll show you with an example that the answers are pretty much the same thing. Let's go to the experiment. In this experiment, I'll be showing you that the functions that we saw earlier in the video in fact compute the same thing. Let's get started and import NumPy. Now we have the weight matrix, the weight vector. As you can see, the shape of the weight matrix is 1, 2, and then it has the values 5 and 6. It has one row and two columns. And then we have DZ. DZ is of the shape of 1, 1. It has one row and one column, and the number it contains is 5. Now this is the first method that we saw in the video. We directly multiply the two results. We have 1, 1 and we have 1, 2. If we multiply these two, we get 1, 2. Yeah, see, we have 1, 2, and then this 5 is multiplied with this 5 and this 6, and we have the array to be 25 and 30. Now when we transpose this, we get the answer 2, 1, and the row vector turns into a column vector. And this is the other method, the alternate method. And this is the commonly used formula. So this computes the same thing. So what this formula does is it transposes W, and then it does matrix multiplication with the Z matrix, DZ matrix. Now from the experiment, you are very sure that no matter what method you use, the final objective, the final goal is the same thing, that you have to bring this to the same shape as A1. Now since we brought this to be 2, 1, we can write it here and then verify this. Our next task will be to compute the gradient of A1 with respect to Z1. So the tan h, the gradient of tan h is nothing but 1 minus z1 the whole square. And then the last term, the gradient of dz1 with respect to dw1 is nothing but a naught. So if you differentiate this term with respect to w1, you get x naught. X naught is a naught, right? So before this, we need to verify the shapes. So this term, we coming here, we are done with this, we got done with this, now we are here. This whole term is dz1. So z1 and a1 are the same thing, so they have the same shapes. Now we have to calculate, we have to make sure dz's shape is also 2, 1. How do we do that? We write down the shapes of dz1 here. So we write the shape of this one, which is 2, 1. So now when you multiply these two, this is element wise multiplication, and we will get the term 2, 1. So if you notice, we are performing matrix multiplication in some places and we are performing element wise multiplication in some places. Why is that? So it doesn't matter what type of multiplication you do, it only matters to match the shapes of what you want. So in our case, we want this dz term to be in the shape of 2, 1. So we are performing element wise multiplication here to get 2, 1. Now since we got dz to be 2, 1, we take this off. And then finally we have a0. We write the shape of a0. a0 is 2, 1. Now our goal is to find the full terms derivative. Alright, so the full terms answer is dw1. Alright, so dw1 corresponds to w1. So ultimately dw1 will be subtracted from w1. So they should be of the same shape. Alright, w1 is of the shape 2, 2. So we want dw1 also to be of the same shape, which is 2, 2. Let's see how to get that. So we have 2, 1 here, and we have the shape of a0 to be 2, 1. If we multiply it element wise, we'll get 2, 1. But that is not the answer we want. We will be needing 2, 2. So for that, we will transpose this a naught. So when we transpose the a naught, we get 2, 1 into 1, 2. This will give us the answer 2, 2. So the final objective is achieved. So if you take these two terms, you keep it as it is and take the transpose of this, you're left with 2, 2. And then the final gradient of the loss function with respect to w1 is obtained. So next step is to compute db1. So db1 essentially follows the same path till z1. So you can write it as dz1 into, okay. So now note that this dz1 and this dz1 are not the same thing. This corresponds to dl by dz1 into, this is the differentiation of this function with respect to b, which is 1. So what is dl by dz1? We have it here. dl by dz1 is here. So you cut A, Z, Z, A1, A1. We have DL by DC1. So until here, the answer is here, 2, 1, which is A2 minus Y into W2 transpose, and then 1 minus Z1 the whole square. So to write it a bit clearly, A2 minus Y into W2 the whole transpose into 1 minus Z1 the whole square. Let's verify. Z1 the whole square. Yeah. So this is the answer for DB1. Since we have computed DW1 and DB1, we can cross this off here. Now since we have computed the gradients, it's time to verify. If you're following the neural network course on Coursera by Deeplearning.ai, you can find this material there. Andrew and G gave these formulas, and let's verify it with the formulas that we derived. Now we have dW2, which is A2 minus Y into A1 into T, and if you compare these two, it is the same thing, only that we have substituted this here. So we didn't essentially find DZ. So you have to do this in order to implement this on code, but to understand the concept, I think it's better if we expand all the terms here. And then to compute dB2, it is the same thing as dW2, only without the extra multiplication term. And coming to the first layer, the first layer has this big term and then multiplied with A0. So this is essentially the same thing as this. If you see DZ1, you have dW2 transpose into DZ2. DZ2 is A2 minus Y, element wise multiplication, into 1 minus Z1 square. So this term corresponds to this term. Since our activation function is tan h, the derivative of the tan h function is this. So we got dz here, and we have a0 transpose here. They have used x. Since we have used x to be equal to a0, we have a0 transpose. And we also saw that there isn't a significant difference between these two terms. They compute the exact same output. So when you know what is the answer that you want, what is the shape of the answer that you want, it actually doesn't matter which formula that you use. You won't have to memorize the formulas or memorize the numbers. If you know, then you know. Yeah. And then coming to the bias term, you have the same term here, only without the multiplication term. Thank you.